In this paper, we present a self-supervised method for learning temporal dynamics from cycles in narrated video. What is the ideal prediction of the future? Well, we'd like for this prediction to be dynamic, rather than at a fixed offset into the future, since interesting things happen at varying durations in time from the present, depending on context. We'd also like this prediction to be high level. For example, given a visual state of someone mixing eggs and flour, we might want to predict that they're next going to roll out some dough. Finally, we'd like for this prediction to be unsupervised so we can scale to the large data sets of diverse, unlabeled human action that have recently been released. Concretely, consider this image of someone pouring mix into an ice cream churner. We don't want to make predictions at time t+1, since these are often low-level and only depict stochastic motion. We also don't want to predict an arbitrary frame into the future, since these often show uninteresting and unrelated futures, such as the one shown here in frame C. What we'd really like is a model that can map from frame A to frame D, which is this interesting transition of you're pulling the paddle out of the ice cream maker and you've ended up with soft serve. This is the sort of intuitive temporal transition that takes place here. Training a model to fulfill all these desiderata is a challenging task, and the choice of data is as important as any. We choose to focus on narrated instructional video, which shows long transitions through time and also provides weakly aligned textual explanations for what's being depicted in video. Here we show an example of sampled frames from such a video and their corresponding narrations. Note that in practice, data is much noisier than this often. We begin by representing each frame and each utterance as a node in a graph. We propose a multimodal cycle consistency task on this graph, from which we hypothesize a high-level predictive model of the future will emerge. Specifically, we begin the cycle by giving the model a starting node in the form of a randomly sampled frame or textual utterance. From this start node, the model selects corresponding information in the other modality, here a textual utterance. Importantly, the model does not see timestamp information about its inputs. It has to learn a cross-modal correspondence function and find the text that co-occurs. This is helpful since in practice, the most relevant text is not always at the exact same time. The video frame and text together comprise a start state. From this start state, we task our model with predicting some future image, which is then augmented with text similarly to comprise a future state. Note, though, that this alone is a very ill-posed problem. Even without temporal information as ground truth input, the model can still choose to learn to predict the future of, say, food on a table, which is almost guaranteed to take place in the future. This future prediction therefore must be constrained. The constraint we choose is that from the future state, we must be able to learn a predictive model of the past that undoes the future, such that we cycle back to the original start state. This cycle consistency loss is depicted in orange here. To understand the motivation behind this cycle loss, let's reconsider this ice cream example and understand why only D can emerge as a viable solution to our cycle problem. Remember that our model needs to find temporal cycles in both vision and language. This disincentivizes the model from making predictions that occur in the immediate future, since the model is not going to predict as a future the same textual state that it's already at. Instead, the model is biased toward attending to transitions that are salient in both modalities, and these tend to be more high-level and aligned with human intuition. A future frame such as C does have different text and visual appearance, but the model would not be able to find its way back to A since these two states are unrelated. Our constraint forces the forward and backward in time predictors to agree on a policy for prediction that's fixed based on the context and can thus be undone. D indeed is a solution to our cycle constraint. The states are related, meaning that the future prediction can be inverted to close the cycle. The transition is also shared across video and text, satisfying the multimodality requirement. In practice, we implement each cycle edge as an instantiation of soft attention, a differentiable version of hard selections of nodes, to facilitate training. Here we show some examples of cycles discovered by our model, given the start node shown in the left column. The model finds pertinent information in the other modality, makes predictions about a relevant future state, and then is able to close the cycle to get back to where it started. We also show examples of cycles with visual start nodes. We're also able to deploy our model on all pairwise transitions in a video to find the most salient transitions according to our model's learned probability function. The model discovers such transitions as segmenting an orange, adding chocolate chips to dough, and stirring up a salad. We can also use our model's learned function to temporally order collections of images by inducing a fully connected bidirectional graph and finding an optimal path in it. Finally, we show that unsupervised action and object neurons emerge through training.